So, what if the solution to one of our biggest global challenges was hiding on the back of a tiny beetle? Seriously, today we're going to dive into how nature is inspiring a technology that could literally pull clean water right out of thin air. First, let's get a handle on just how massive this problem is. Right now, over 2 billion people, that's about 1 in 4 of us on the entire planet, live in countries dealing with serious water stress. It's a huge, staggering crisis, and it's not getting any better. I know, it sounds a little like magic, doesn't it? The idea that we could just grab the water we need from the atmosphere around us. But here's the thing. This isn't magic. It's a brilliant piece of biology that we're finally figuring out how to copy. And to do that, we have to meet our tiny little instructor. We're heading to one of the driest places on Earth to uncover the secret of the Namib Desert beetle. This little creature has absolutely perfected a survival trick that we really need to learn. Okay, just let that sink in for a second. Only 1.4 centimeters of rain a year. That's less moisture than you'd get in a single thunderstorm in a lot of places. And yet, this beetle is doing just fine. So how on earth is that possible? Well, it doesn't wait for rain. It goes out and makes its own drink by harvesting fog. And this is where the genius really kicks in. Every single morning, this beetle does this amazing little ritual. It scoots up a sand dune, angles its body perfectly into the breeze that's carrying the fog, and its back does all the work. You see, it has these tiny water-loving bumps that grab moisture right out of the air. Then, as the droplets get bigger, they roll down these waxy, water-fearing channels straight to its mouth. It's a flawless, zero-energy water collection system built right into its shell. So, the beetle's whole secret comes down to this incredible push and pull happening on its back between two totally opposite properties. To really get how we can copy this, we gotta dive into the science of what makes these surfaces tick. So first up, you've got those bumps on its back. They're hydrophilic. The easiest way to think about this is like a paper towel. It's basically water-loving. These surfaces have a chemical pull that attracts water molecules, convincing them to stick around and start forming little pools. But then you've got the channels in between, and they're the complete opposite, hydrophobic, or water-fearing. This is that classic effect you see with oil and water. These surfaces push water away, forcing it to bead up into tight little balls that can roll away with almost no effort. It's this brilliant 1-2 punch of grab and release that makes the beetle's back so unbelievably good at its job. And you can see that exact science right here. Look at the left. A water droplet on a hydrophilic surface just flattens out and spreads. But on the right, on that hydrophobic surface, the droplet beads up into a near-perfect little sphere just ready to roll. That high contact angle is the secret sauce for getting the water to move efficiently, just like it does on the beetle. So naturally, scientists had this amazing thought. Hey, if a tiny beetle can do this, why can't we? And so they set out to not just copy nature's design, but to see if they could actually make it even better using some seriously cool modern technology. The first step? They started 3D printing a whole bunch of different surfaces. We're talking about tiny cones, pyramids, cubes, all designed to mimic the bumps on the beetle's shell. They wanted to run an experiment to see which shape was the absolute best at grabbing water droplets out of the air. And wow, the results were pretty mind-blowing. This chart just shows the data for the cube shapes. A normal flat surface collected around 312 milligrams an hour. Not bad. But look, make that surface into tiny hydrophobic cubes, and the amount collected doubles to 625. But here's the real kicker. When you add those special hydrophilic water-loving tips, just like the beetle, it jumps again to 735 milligrams per hour. Incredible. Actually, get this. The absolute best design they came up with, that cube shape with the hydrophilic peaks and hydrophobic base, showed a jaw-dropping 270% increase in fog harvesting power compared to just a regular flat surface. That's what happens when you nail the perfect combo of shape and surface chemistry. Okay, and this is where this whole thing becomes so important. To really appreciate what a game changer this is, you have to put it side by side with how we currently make fresh water, methods that, frankly, have some pretty big problems. This table lays it out perfectly. On one hand, you have traditional desalination, which turns seawater into drinking water. It's a total energy guzzler, costs a fortune to build and run, and it produces all this nasty, super salty waste called brine. But then you look at the beetle-inspired fog harvesting. It's completely passive. It needs zero external energy, it's low cost, and it's environmentally friendly. It's just a smarter, more sustainable way of thinking about water. So all of this brings us to the really exciting part. What could this actually look like in the real world? We're talking about going from a tiny beetle's back to a solution that could provide clean water for entire communities. And here it is, the big payoff. Researchers figure that just a single 1 square meter panel using this new design could, in just a few hours in a foggy area, collect enough water to cover one person's daily needs. I mean, just imagine that. A simple, flat panel providing all the water you need to drink, to cook, to clean. This isn't some lab experiment anymore. This is a real, practical, life-changing technology. It just makes you wonder, right? The key to a global water crisis was inspired by a tiny insect just trying to get a drink in the desert. It's such a powerful reminder that sometimes the most brilliant answers to our most complicated problems are hiding right in front of us, just waiting for us to pay attention. So, what else is nature waiting to teach us?